let's start where I think the story began for us already. I showed you a way to do something. If you don't recall, let's at least start with this. In the hopes of never having to do this again, I'm starting with something I don't want you to do again. There, looks familiar? One of those? We know what this object is doing now, right? After careful study, we figured out that this object's velocity is increasing in a regular way. Does that make sense? And we know that the object started at a positive velocity and that over time that became a more positive velocity. We learned several things about this function. For example, we learned that this slope matters. That if it was a steeper slope, the velocity was changing at a faster rate. Shallower, a less steep slope, the velocity is changing at a less fast way. We learned that this object is speeding up, and we can tell that not because of the slope as much as where it starts and the slope. Because if we had this graph, they may have the same slope, but one of these objects is slowing down and one of these objects is speeding up. We understand that we can't tell the difference just from the slope. We need one of the starting or ending points. Now, we also found that there's meaning to the values here, and there's also meaning to the area here. Those were the mathematical tools I used to help us figure out how the velocity was related to the position and how the velocity was related to the acceleration. We used the tools of algebra to come up with a method that would give us the shape of a position versus time graph, right? You could look at the velocity versus time graph right now, and you should be able to come up with a position versus time graph. Assuming the object started from the origin, you'd probably say, okay, it has some positive slope at time 0, that's this point. And after some amount of time, it has a steeper slope. And yes, we've done this before. This is not exciting. Oops, not great. Let's do better. Something like that. We know that we can't count on this point. We don't really know where the object starts. It's not contained within the velocity graph. That's an initial condition we don't know about. At the same time, we could evaluate the slope of the graph for velocity and come up with another function, an acceleration versus time function. And for this one, that'd be pretty straightforward because it's a constant. It looks like that. Now, we did more than this, right? This is just scratching the surface. We eventually developed the fact that, well, if this is linear, then by looking at the area and combining this relationship with the relationship for the area, we could predict that this relationship had to be quadratic. And that's what we did. Now, it took us 3 weeks to kind of come up with that, but that's what we derived. Now, that's a way around, isn't it? Not particularly elegant, was it? And took lots of algebra. This was us using the tools we had to do a job that can be easier done with calculus. But this was the tools we had, so it wasn't elegant. And it only worked in this case because we narrowed the rules, right? You could only use that flathead screwdriver to unscrew that Phillips head screw if the flathead fit inside the cross for the Phillips head screw. You guys know what I'm talking about? If it's any bigger than that, you're not really going to be able to use it, are you? You try and get it in there at an angle and you just destroy the screw. So it worked in very narrow circumstances. The moment we change the rules a bit, what if instead I tell you that your velocity is this function? This could be a velocity versus time graph. I can imagine speeding up and slowing down and speeding up again. And I can imagine doing it in a way that was smoother than just some jerky, instantaneously stop and go backwards, instantaneously stop and go forwards. And this object is going forwards the whole time. But could you, looking at this, come up with the position versus time graph? It would be harder, wouldn't it? We know that the position versus time graph is a graph of the slopes of the velocity graph. So if I was to start here, I'd say, well, the velocity is small, so that would be shallow. And the velocity here is something greater. So a few seconds later, my velocity is going to be like this. But here, my velocity is even greater, still going forwards. So now it's even steeper. But now my velocity is less again. And now my velocity is less again. And now my velocity is small, but still positive. But now my velocity is starting to grow again. You understand how much difficult this is going to be? And this is assuming I know where to place this portion, how far away it's moved. I'm not convinced I was doing that particularly well. I'm not sure what this function is going to look like, but you see the difficulty in doing this. Not to mention, if that's my position graph, well, my acceleration graph, every time the acceleration is positive, every time the acceleration is negative, that's the slopes of all these lines. Here I try and look at the slopes and then plot the slopes here, where I took these values and created slopes there. Here I'm taking tangent lines and finding their slopes and putting them here. I don't know that algebra is particularly suited to do this. That's why a new math was created. Now, here's what I want you to understand. The derivative and the antiderivative can take a function, any given function, and help you move from one of these to the other by not looking at the graphs, but by just looking at the function. Now, to understand 2x to the fourth in any generic sense, and I'm going to start by putting the word up here, derivative and antiderivative. The word derivative has other meanings outside of physics and outside of calculus. So I'm interested in the meaning directly related to calculus and physics. We'll start with the derivative. The derivative of a function creates a new function that is the slopes of the original function. That's just a big mouthful of words, isn't it? I'll say it again, but knowing this is not necessary. The derivative of a function gives you a new function that is the slopes of the original function. Now listen closely to this. When we had our velocity versus time graph a moment ago, the slope of that straight line graph that we had was what we used to figure out our acceleration versus time graph. We looked at the slope of this function, saw that it was a constant, but that told us what this function looked like. Now, what I'm here to tell you about is that if I have a function, no matter how complicated it is, the derivative of this function will be a new function that tell me the slopes at every point on this function. It tells me the slopes. So the derivative of a velocity function will tell me the acceleration function. Because that's what we did. Now, you may not fully appreciate that, and that's okay. If you don't fully appreciate it, at least to help you with that, I want you to think about what slope is really about. If I have a graph of any function, and I plot it on the y and x axis, my function, y as a function of x, returns a value for y whenever I plug in a value for x. Right? If I have y equals 12x to the third minus 2x to the negative 4 plus 4x squared. If I ask you to tell me what tell me what y is when x is 2, you could quite easily plug 2 into this function and tell me what y equals. Does that make sense so far? Now, I don't know what this function looks like. I really don't. But I do know that it probably is a curvy function. And with that being said, that probably means that its slope would be always changing. Now, I know that if I just pick a point on that line, or maybe 2 points on that line, no matter where they are, the old way of finding slope is to take those 2 points and find how much the y portion of that function changed and divide by how much the x portion of that function changed. We're good at that. That's why we could use straight lines. Would you be able to do that for this? And do you think that every single location would have the same slope? No. The derivative creates a function that tells you all the slopes. But since it is slopes, math wants to use the same kind of terminology. So we will use symbols that are similar to the delta here. We will say that the derivative of y with respect to the variable x will be communicated to you by this symbology. We will change the deltas to lowercase d's. And those lowercase d's mean we are calculating the derivative. We are going to create a new function that will tell me all of the slopes of the original function. That's why we don't use delta, we'll use d. Now, there's been an evolution to this symbology, and a whole variety of different types of d's have been used. So although we just use standard Roman lowercase d, there's been this couple of just evolutions of different kinds of d's that have been used here in the derivative. Nowadays, these d's are actually used in different types of mathematics, partial differentials and things of that nature, where more than one variable is changing all the time. So the lowercase d is pretty traditional, and that's the one we're going to stick with. Okay? Now, 12x cubed minus and plus, when we talk about applying the derivative to my function. So what was my function just a minute ago? So 12x cubed minus 2x to the negative fourth x squared. I could ask the math to tell me the derivative of my function. Now, this is an operator that tells me to take the derivative of the y function with respect to the variable x. That's what that tells me. So when I write this down, I'm communicating something to you. I'm saying take the derivative of the function of y with respect to the variable x. It is possible to use the derivative as an operator, which means you can take the derivative of both sides of an equation. Now, the left side is nothing interesting. Y is the function. So we would just write the left side as dy dx. But the left side is a polynomial. And because it's a polynomial, there's something I must do to the polynomial in order to find the derivative. Now, here's where I have just a bit of an aside. Let's try it here. The first thing you must know, the derivative obeys the distributive property. So I can distribute this to each term and apply it individually. Now, if I was a better teacher, I would write out every step here. I don't really want to, but I'm going to the first time. I'm going to say we're going to do d dx of 12x cubed minus d dx of 2x to the negative fourth plus d dx of 4x squared. All right, so bring out my coefficient first, 12, and then I'm going to act on my x cubed by bringing my 3 down and taking 1 away from the exponent. I'm kind of doing 2 steps at once. I brought the coefficient out, and then I applied the derivative to what was left inside. Same thing here, right? I'm going to bring my coefficient out, and apply my power rule. I'm subtracting 1 from the exponent, so in this case, I subtracted 1 from 4, and I got 5, because it was negative 4. What's that? Oh, yeah, I'm sorry. Skipping ahead to something I want to do in a minute. Now that you've done this, just clean it up. This is 36x squared plus 8x to the negative fifth plus 8x. This is a function that is now the slope of my original function. These functions are related by the derivative, but they are 2 separate functions. This is why calculus is often called the algebra of functions. If algebra shows you how numbers are related, calculus shows you how functions are related. So, let's see this in action. Delta x equals 1/2 a t squared plus v naught times t. Let's write this as a function, meaning let's take the delta x and remind us that's x minus x naught. And let's move that x naught to the other side because that's a starting position. Now, the important variable here is x and t, right? If we were to plot this, x would be on the vertical axis and t would be on the horizontal axis. If I wanted the slope of this graph, then I would want to take the derivative with respect to t of my function x. This should give me the slopes. Now, I think that this is something we can do without all the steps. Can I distribute this and try it first here? 1/2 a is my coefficient. And I'm left with t squared. Bring down the 2 times t to the 2 minus 1. Go on to the next term. Is that okay? You guys follow that all right? So now let's try that term. Bring out the v naught. And inside I'll have 1 times t to the 1 minus 1. We good so far? Now, I know that that's the bell, but I need you to see something here. You notice there's no t here, correct? That means there's an implied t to the 0 power. So, bring out my coefficient. 0 times t to the 0 minus 1 power. Now, this clearly goes away. 0 times anything is 0. But look at what we're left with. What is 1/2 times 2? A times t to the 2 minus 1 is t to the 1 power, correct? Plus, 1 times v naught is just v naught, and what is t to the 1 minus 1? What is that? It's 1, right? Because that's t to the 0 power. Now, here's the important thing. We knew this before we started. This is dx dt. By definition, this is how much the position changes as a function of time, which we defined it as the rate of change of position. What is that called? Does that look familiar? Do you guys see the familiarity there? All right. Polynomial is a function. It's a type of function, though. There are lots of types of functions. You are probably aware of the general form of a polynomial. Right? A polynomial is anything that has multiple terms where there is a single variable of importance that is raised to different exponents. So I've chosen to make this one sequential, but this is a polynomial to the 4th power because the biggest power in my polynomial is 4. But there are lots of functions. If that's one function with y, well, there's other functions with y in them. There's another function, right? Not a polynomial, right? That's a trigonometric function. There's exponential functions. There's logarithmic functions. And you understand, we could do this all day, right? For every different kind of operator that you're aware of, there is a different function we could talk about. Calculus will teach you how to take derivatives of all the different kinds of functions. And calculus will teach you how to mix it up, right? You could have x squared e to the x sine of omega times x. Boy, that would be fun. There is probably a tool in calculus, and there's several tools in calculus, that would let you say, okay, you've got a whole bunch of functions there. Have fun. Find the derivative. Product rule, probably what I'd use here. So I'm saying this to you because these 4 basic functions, plus the product rule, are things I want you to learn. Today, we're just learning one of them. We're just going to learn the polynomial rule. And to understand the polynomial rule, I want to teach you what the polynomial rule is. The polynomial rule does exactly what I just said it does. It applies to a polynomial. So if I have a polynomial, and let's just look at one nomial of the polynomial, y equals ax to the n power. This is one term of a polynomial. If I want to take the derivative with respect to x of my polynomial, there is a procedure. Now, this only works on polynomials, and it only works on certain polynomials. There are limits to the polynomials in which this will work. But it does work, and it's pretty easy. The polynomial rule is super simple. First, this letter in front of the x is called a coefficient. Because my derivative is with respect to x, x is the variable that's important. X is the variable to which we are taking the derivative. That means everything else is considered a constant for the purpose of this derivative. Does everybody understand that? Everything else is considered a constant for the purpose of this derivative. If the other variables are changing when x changes, you need a new kind of math called partial differential equations, which we are not doing this year at all. But if all you want to do is take the derivative, if only one variable is changing, then the polynomial rule is for you. First, coefficients. They can be brought out front of the differential. So the first thing I would do here is I would tell you that this is actually a times d dx of x to the n power. Now we got that pesky coefficient out of the way, we are going to employ the polynomial rule. The polynomial rule is super simple. To employ the rule, we take our exponent and bring it down front to become a new portion of the coefficient. We then subtract 1 from the exponent. That's it. That is the polynomial rule. Not particularly interesting. Now, you can clean this up, I hope you know. I could recognize that it's just a times n times x to the n minus 1. This would be my derivative.